Hi everyone.
Today we're going to solve a second order parallel RLC circuit.
We're going to assume that this switch has been closed for like all of time from negative infinity until zero, and then at time is equal to zero, this switch is open, and then from now on, the switch is open. So Seven, how do we start solving a circuit like this?
Well, let's draw it before the switch is closed and after the switch is closed, and
Okay.
then that'll give us an idea of the initial conditions and some of the other stuff going on.
hmm
So, Sid, what's it look like before the switch is closed?
So before the switch is closed, before the switch is open, sorry, it looks something like this. That's a resistor, a capacitor, and an inductor.
Great.
Then,
And so this is for t is less than 0, right? So for t is greater than 0,
and for t greater than or equal to 0, it looks like this. Cool.
well, we want to figure out, I guess the first step we want to do is we want to figure out what the initial conditions for this thing is, right?
Okay.
So at t is less than 0, this we're looking at for steady state.
What do you mean by steady state?
Well, we know that it's been like that since the beginning of time, since negative infinity to 0.
Okay.
And so we know that the circuit has sort of settled to steady state values. And for that reason, we look at the behavior right before and right after the switch is closed.
So is it a good way? Is a good way to think about it that until we change the switch, if we don't, the circuit would just stay in its current state from now till infinity.
That's fair, yeah.
Cool.
At steady state, what does a capacitor become? Once a capacitor charges up and it reaches a steady state voltage value, then there's no more current flowing through it, right? So we like to model that as an open circuit.
So what's the initial state of an inductor then?
Well, an inductor at steady state, acts like a short circuit. It acts like just a wire.
And why is that?
It's because once an inductor is charged up, unlike a capacitor, it just becomes a wire. Once it's stored all of the necessary energy in its magnetic field, it no longer provides any impedance or resistance to the circuit. So if we were to redraw the circuit for t is less than 0, given these steady state conditions, it would look something like this. So this capacitor becomes an open, you still have the resistor, and your inductor becomes a short.
Cool.
And this is your VL, VC, and VR, which are all equal. And then you have the three currents going through them.
Cool.
IL, IC, and IR.
So what's IC?
IC is the current going through the capacitor. And because we know that it's in steady state and it acts like an open, we know that IC of 0 minus being right before the switch is closed, by the way, this is a C, is 0.
Awesome.
So, Sid, IC is 0. How about the other ones? Well, is there any voltage difference for VL if it's just a short circuit?
No, is what I want to say.
Yep, that's correct. So VL of 0 minus is 0.
Cool.
There's no voltage difference because it acts like a short.
Awesome.
So IC is 0, VL is 0. So if VL is 0, then what about VR and VC? Those two should also be equal to 0 at 0 minus.
Cool.
All right, so if VR is 0, then we know that IR should also be what?
0.
0, right? If there's no voltage across the resistor, then there is also no current through it.
Which law tells us that?
That's Ohm's law.
Amazing.
So IL of 0 minus, well, what can we say about IL right beforehand? And this is a current I.
Well, so if I apply KCL, or like a similar idea, to this node, let me just change colors. If I apply KCL to this whole region, I see that there's a current I coming in, this current is 0, this current is 0, So this tells me that whatever coming in has to come out over here at the same rate.
Perfect. So how would you write that as an equation?
Cool. IL of 0 minus is equal to I.
Yeah, so what I was going for is the KCL equation for that node.
Oh.
For the upper node, I equals IR plus IC plus IL.
Awesome.
CL. I. Great.
Cool.
And because, therefore, IL has to be equal to I.
Awesome.
So now we have our initial condition.
What about the second initial condition? What would you do for that?
We have two components that sort of give us our initial conditions here. We have IL. We know that IL, after a time as t is greater than 0, must retain its value for that split second right afterwards. And we know that VC of 0 right afterwards must retain its initial value. So what we can say is that we know for t is greater than or equal to 0, we know that VC of 0 minus equals VC of 0 plus. And we know that VC of 0 minus is equal to 0. So this is 0. And we know similarly that IL of 0 minus equals IL of 0 plus equals I.
Okay. That makes... Is it because the functions are continuous or expected to be continuous that this is true?
Yes. Cool. So we know that the inductor current and capacitor voltage must be continuous. So those must retain their values before and after the switch is closed immediately.
Awesome.
However, we can't say anything about the inductor voltage or the capacitor current. Those two are not defined. They're only defined by our circuit. What we're going to solve for here is we're going to solve for the inductor current.
Okay, that makes sense.
So we're going to make a second order differential equation for the inductor current. So we know that IL of 0 plus is equal to I, and we know that VC, which is equal to just, VL is equal to VR because they're all the same node, of 0 plus is equal to 0.
Awesome.
And so that'll help us out.
How?
Well, that'll let us solve for the initial conditions for all of the other points in the circuit and let us relate the values.
Wait, I have a question. Why did you choose IL? Why couldn't you have chosen the capacitor voltage or the current through the resistor?
I could have. I just decided to use IL. You could have equivalently made similar equations with IC or VC or IR. So now that we got that, we can figure out, we can start solving the circuit. If we're solving for IL and we want a second order differential equation for IL, we also need to know the derivative of IL, right? So we want to know d dt of IL at 0 plus, right? So to solve for that, we're going to have to use our other initial conditions. So the second initial condition we can note from some of our inductor properties. So we know for an inductor that VL equals L di dt, right? We also know that if VC is equal to VL is equal to VR is equal to 0.
At time 0 plus?
At 0 plus. We know that this must be 0 equals L di dt of 0 plus. Therefore, we can throw that up in here, and this is just 0.
So what we're going to do next is we're going to apply KCL to this node right here. So now since all of these are connected by a wire, this whole thing is basically one node. So recall that this is IR, this is IC, and this is IL. By KCL, we have IR plus IC plus IL is equal to 0.
Perfect.
Cool. So what's IC, Salman?
Well, IC is the current going through our capacitor, is C dV dt, right?
Cool.
And then we can say that,
What
so
is
let's
the V
use that.
there?
Sorry?
What's the V?
It's the voltage across the two. the only voltage here, basically, which is just VL is VR is VC. Okay, so we got IC equals C dV dt. We know that V equals L DIL dt. And so we can use this, substituting in. So we know that IC equals CL D squared IL dt squared.
Awesome.
So plugging that in, we have IR plus plus CL D squared IL dt squared plus IL equals 0. All right.
What about IR?
Well, we're going to have to figure out a way of doing that. So what we can note here is that IR, by Ohm's law, we know that, V equals IR times R. So divide by the R, and you have just V over R. And then plugging in our relation for voltage from above, we can note that, so this is IR equals that, equals L over R DIL dt.
Cool.
So putting this all together, our differential equation is CL d squared IL dt squared plus L over R DIL dt plus IL equals 0.
Cool. And now, just as a standard step, if you look at the lecture notes, we tell you how to get. So when you construct the A matrix from this differential equation, we tell you how to get the eigenvalues directly. And in order to do that, you first need to reduce it into this basic standard form, which is basically to make sure this has coefficient 1. So we divide this whole equation out by CL, and we get d squared IL over dt squared plus 1 over CR plus 1 over CLIC is also DIC over dt.
It's DIL dt.
DIL dt. My bad.
Great.
Cool.
So that is our differential equation.
In order to solve this differential equation, we will first construct the A matrix as it was called in lecture. So we're going to define a vector that looks like DIL over dt, DIL over dt squared is going to equal to some matrix times IL and DIL over dt. So Savan, can you fill in the top row of the matrix?
Sure. So if we were to write this out, we would realize that you're just multiplying this first row by IL and DIL dt, and we're trying to find what sum gets us this back. If we note, DIL dt is just this, which is DIL dt is equal to DIL dt.
Awesome. And now, in order to get the second row, we're going to use this equation above. So, as you can see, this term right here is equal to the minus of this term and the minus of this term. So, plugging that in, we get minus 1 over CL and minus 1 over RC. Cool.
Great. Now we solve it.
If I wanted to find the eigenvalues of this matrix, I'm just going to call A. What's the first thing we should do?
Well, we want to construct the determinant of the eigenvalues minus this.
Cool. So that looks like the determinant. The determinant of let's do A minus lambda I. If you do lambda I minus A, it's identical because since we're equating it to 0, it doesn't really matter. So what that looks like is minus lambda 1 over CL and minus 1 over RC minus lambda is equal to 0. So the determinant of this is equal to 0. Minus lambda times minus 1 over RC minus lambda minus 1 of minus 1 over CL is equal to 0. So, can you please expand that for me?
Sure. So we end up with lambda squared plus lambda over RC plus 1 over LC equals 0.
Hey, wait a minute. These equations look identical. What gives?
Well, it turns out that if we construct it the right way, they are identical.
Cool.
This is referred to as the characteristic polynomial of that differential equation.
And the determinant of a matrix, like what we did here, is often called the characteristic equation of a matrix, which is coincidental.
Yeah.
Okay. Cool.
So solving this out, we end up with using just our good friend, the quadratic equation. We have lambda equals minus 1 over RC plus or minus the square root of 1 over R squared C squared minus 4 over LC all over 2.
Cool. I'm probably not going to check you on that right now. I'm going to assume you're correct.
Yeah, negative b plus or minus the square root of b squared minus 4ac.
Okay, cool. Now,
reducing this a little bit, let's bring this 4 up.
Okay.
This 2 rather. Minus 2, minus 1 over 2RC plus or minus the square root. So bringing the 2 up, you have 1 over 4R squared C squared minus 1 over LC.
Okay, so now since you're working with circuits, there are terms that we often use, such as overdamped, underdamped, and critically damped, and we're going to show you what they mean. So let this term be alpha. Observe that this term is alpha squared, and we're going to define this term to be omega squared. So omega is going to be 1 over square root of LC.
And then alpha is...
Yeah, right. Alpha would be minus 1 over 2RC.
Cool.
Great. So if you look at this part, you can see that there are 3 things that could happen. I'm going to make it in a little box. One is when alpha is greater than omega, one is when alpha is equal to omega, and one is when alpha is less than omega. Salman, tell us what happens in each of these cases.
Well, there are 3 different cases that we call them 3 different things. So if alpha is greater than omega, then this is a purely real eigenvalues. This is where purely real eigenvalues. And this is what we call the... I don't know why it's just... So the purely real eigenvalues, and we call this the overdamped case. For this, for alpha equal to omega, we can note that the determinant just ends up being 0, and we call this critically damped. And then finally, for alpha is less than 0, this is underdamped. And this implies that you have complex eigenvalues.
What does that mean? I mean, how can we have complex values? It's called an imaginary number. How is that real?
Well, it represents something a little bit more. It represents that this sort of does not look purely like an exponential. It represents that it has sinusoidal behavior or varying behavior.
So we have eigenvalues that look like alpha plus or minus square root of alpha squared minus omega squared. And we're trying to solve for IL.
Perfect.
What does the general form of a second order differential equation look like, roughly speaking?
The general form of a second order differential equation.
Like a solution.
Well, if it's not critically damped, so if alpha does not equal omega, then we know that this yields us, in our special case, IL is equal to K1 e to the lambda 1t plus K2 e to the lambda 2t, where lambda 1 and lambda 2 are the 2 values for our eigenvalues, plus or minus.
Cool. And what are K1 and K2?
Those come from our initial conditions, which we calculated before. And we can go back at the very end and figure out what those will be.
But what if alpha is equal to omega?
Then we have to deal with our critically damped case. So if alpha is equal to omega, we can note that there's only one eigenvalue. And that eigenvalue is just alpha. And if alpha is equal to omega, then we get IL equals to K1 T e to the lambda T plus K2 to e to the lambda T.
So later in the course, we'll like really understand how we get this solution, like how we derive it, but we'll never really go into why this is the case.
Just trust us that this works.
You can verify it by using the fundamental theorem of differential equations as in your homework, and that's pretty much the proof that you need. Okay, now that we have the general form of a differential equation, how do we know which? So if you have no numbers, we can basically assume one of these two forms and make an argument that it's going to be one of those forms.
Mm-hmm.
So for now, just to keep the video a little short, we're just going to assume the solution is of this form,
Great.
the one on the left, and we're going to get rid of this. Cool. What do we do next, Alvin?
So if we assume it's of this form, we basically want to plug in values to find the initial conditions.
Okay.
So to do that, we remember that we found that IL of 0 plus is equal to I, and then DIL dt of 0 plus is equal to 0.
Mm-hmm.
From there, we can find the equation. So IL of 0 is equal to just K1 plus K2.
Mm-hmm.
DIL dt of 0 is equal to lambda 1 K1 plus lambda 2 K2.
So as you can see, here's another example on why we would need to consider the case when the lambdas are equal. If the lambdas are equal in this case, we'd basically be getting the same condition. So this is saying K1 plus K2 is something else, and this would say K1 plus K2 is equal to something else divided by lambda, which is inconsistent.
Right. Yeah, so solving these, we get if this is equal to I and this is equal to 0, we can say that K1 is I minus K2. Plug that in this guy. Lambda 1 is lambda 1 times I minus K2 plus lambda 2 K2 equals 0. And then just moving things around. Sid, do you want to help me with the algebra?
We are not going to do the algebra. I think that works much better. Roughly speaking, we're just going to use these initial conditions to solve for K1 and K2. An easy way to solve it, if you wanted to look at it, would be 1, 1, K1, K2, lambda 1, lambda 2 is going to be equal to your initial conditions, so which is I and 0, and then we're going to leave it up to you to solve this. I'm a mean person sometimes.
What a
I'm sorry,
scam.
so. It is a scam. Cool. So now let's assume we have K1 and K2. That pretty much solves the equation.
It does.
But-
However, we still want to look at graphically what's happening here.
Okay.
So what we want to remember is that if IL of 0 is I, we want to have some sort of intuitive understanding of how the circuit works.
Okay.
So the next page, let's go into what it sort of looks like. So if we remember that our lambda is equal to minus 2 over RC plus or minus the square root of 1 over 2 RC squared minus 1 over LC.
Okay.
Okay. So and then we have that, and then we also have IL of 0 is equal to I is equal to K1 e to the lambda 1t plus K2 e to the lambda 2t. Great. So noting that we have this, we want to look at the 3 different cases and what they sort of look like graphically and note major features about them, right?
Cool.
So you have this alpha value, right?
Uh-huh.
And then you have this alpha squared and omega squared, right?
Mm-hmm.
So we're assuming real values for this, right?
Mhm.
And we have 3 different cases. If for our overdamped case,
Okay.
where alpha is greater than omega,
Okay.
can lambda ever be greater than 0?
No.
Right. So we can say that lambda is always less than 0.
An intuitive way of thinking about it is to think of what will happen to the differential equation if lambda was greater than 0.
Right. You'd have some exponential behavior and it would blow up.
As an example, imagine you had y of t is equal to e to the 2t, which happens if this is positive, which would look something like whee, and you don't want that to happen in real life.
Right. So I will note that this is for real values of R or L and C, right? Yeah. So for an overdamped case, you end up with an exponential that decays from our initial condition of I and decays to something like this.
Okay. In case it's not seen, because the video screen is showing us something different, I'm going to write I here again.
Oh, interesting. Okay. So you got this I here. And this is your current axis, and this is your time. So if alpha is greater than the omega, and we have some values for the lambdas, how fast does it decay?
What's a good way of measuring that, since it looks like it never actually reaches 0 except at infinity?
True. So we want to look at how fast it reaches certain values.
Okay.
Another question, Sid. So you have two lambda values. You have a lambda plus value and a lambda minus value.
Okay.
Where this is the plus term and this is the minus term, depending on if you subtract or add.
Okay.
You'll notice that lambda plus is greater than lambda minus, right? So which one decays faster? Your k1 e to the lambda plus t or your k2 e to the lambda minus t?
Okay, let me think about this. So, what do you mean when you say lambda plus is greater than lambda 0? You're saying that lambda plus is closer to the 0 than lambda minus?
Exactly. So you can imagine that this lambda plus term looks something like an e to the minus t. This lambda minus term looks like an e to the minus 10t, for example.
Cool, that makes sense. So, let's try and figure it out. So when t is equal to 1, this one is going to be e to the minus 1, which is 1 over e. And this is going to be e to the minus 10, which is equal to 1 over e to the 10. And looking at this, since e to the 10 is bigger than e, this would mean that this is the case.
Great.
Cool.
So your lambda plus term is going to be greater than your lambda minus term.
Exactly.
So if you had to define how this function sort of goes down, in general, it's going to go down by your e to the lambda plus t term.
Cool.
So this sort of follows that. Obviously, depending on your k1 and k2 values, it might, at the beginning, one might look bigger or smaller than the other, but the general case is it'll look like closer to the e to the lambda plus t.
So in a lot of the times, they're interested in the asymptotic behavior, because we're thinking of building systems in the long run. So we want to make sure that in the long run things are like, what's the general behavior of this circuit?
Mm-hmm.
Cool.
So in the general behavior is that it approaches t after some value, right?
Mm-hmm.
And so if we look at how fast it really does that, if we think that this goes by the e to the lambda plus t, it has a characteristic time constant that is 1 over lambda. I can't write. Goes like this. So time constant of 1 over lambda plus, and this reaches, after one time constant, it reaches 1 over e.
What's the characteristic time constant? Can you explain that to me?
So it's just the amount of time it takes for it to reach one exponential away. So
Okay.
one multiple of e, or in this case, negative multiple of e.
Okay.
So this is the point here is equal to e to the minus 1, or about 0.67.
Okay. And what would the second time constant be?
That is a good question. I don't remember.
Okay.
After a
Fair
few
enough.
time constants, it starts to reach its value at a faster and faster pace.
Okay. Cool.
Great. So that's our overdamped. Next, let's erase this really quick and talk about our underdamped case. So for our underdamped case, this is where alpha is less than omega and lambda is complex. All right. So if we have complex eigenvalues, we can rewrite our lambda equation as sort of lambda equals alpha plus or minus. I'm going to pull out the complex term and rewrite it as j times omega squared minus alpha squared.
Cool.
All right. So now that we got this guy, we can sort of look at the behavior of its oscillations.
Okay.
So we look at its oscillations. We're going to start off at I, just as we were before, but this time it's going to start oscillating and decaying at the same time.
Why?
Well, because when you have complex eigenvalues, then you have oscillatory behavior. Another way of thinking about it is that the inductor and capacitor sort of store charge and energy, and when they're releasing their charge and energy, they're not going to do it in a linear or even exponential fashion. They might, trade energy. So it might look something like, this.
Cool. Well, it's also a little more symmetric about the axis, but
We don't have
That's
too much
understandable.
space.
yeah.
So there's a few things to look at here. One of the things we want to look at is the period of oscillation. So the period of oscillation is related to the imaginary portion. The period of oscillation is 2 pi. The period is equal to 2 pi over the imaginary portion, omega squared minus alpha squared.
Cool. So another way to think about why it'll be oscillatory is Euler's formula that you did in homework a couple of times ago. That you did a while ago. And if you break apart the complex numbers, you'll find that they decompose into sines and cosines, and then they will work out in such a way that the result is always going to be real, and you're always going to get something that looks like this.
That's true. So another thing to think about is if omega is much greater than alpha, usually this could be like 2 to 10 times what alpha is. If it's greater than that, and this approximately becomes just 2 pi over omega.
So what's a good way of making sure that omega is much bigger than alpha? Like if you had to choose between RC and L.
Well, if L is... So we know that omega is 1 over root LC and alpha is 1 over 2 RC.
Mhm.
So if you have a large resistance term, then alpha will generally be larger. If you have a large resistance term, alpha will generally be smaller, and therefore omega will dominate.
Cool. That makes sense. So if you ever want oscillatory behavior, just put a large resistance.
Yeah. So if you think about it, your LC constant will generally always be your 1 over LC, or your omega will, if you choose reasonable values, will almost always be considerably larger than your alpha value. This is because 1 over LC is generally larger than like 1 over 2 RC in practice, because L is on the order of 10 to the negative like 3-ish. C is usually 10 to the negative 6, but R is generally 10 to like 2 to 3.
Cool.
Just for, reasonable values. So in general, this 2 pi over omega is like a good approximation.
Sounds good to me.
Okay.
What about the critically damped case?
The critically damped case actually looks very similar to the overdamped case, except you just have, it's the fastest decay that is possible for a circuit.
Okay.
One last thing to note is that the envelope at which this decays. So if we were to look at the peaks of all of them, they would follow an e to the alpha t, which is the real portion of our underdamped eigenvalue. How would if I wanted purely oscillatory behavior, what we want to do is we want to make our alpha value equal to 0, right? Because that represents our the real component or the decay component, right? Mm-hmm. So to make alpha equal to 0, what you'd actually want to do is pull out your resistor and make it a open. For R open, you have purely oscillatory.
If you think about if this is open and if you just had this circuit, if you think about it, it's kind of like the capacitor can store energy in one form and the inductor can store energy in another form. So energy gets sent to the capacitor, which then charges, which then dispenses energy to the inductor, which then dispenses energy to the capacitor continuously. And since there's no resistor, there's going to be no power loss. So in a sense, the energy remains conserved. And the steady state of this circuit, just an LC circuit, would be oscillations forever.
Perfect.
Cool. Well, that's our video review. I hope you liked it. Hopefully, the camera will be fixed the next time. Do you have any parting words of wisdom, Simon?
No, not really.
Come on, you can think of something.
Good luck on the exam.
Cool. What happens when you cross an elephant and a rhino?
You end up with Sid?
Elephino.